Hey everyone, and welcome to this explainer. Today, we're embarking on a trip into the microscopic world, and I mean a realm so unbelievably tiny that you can't even see it with an ordinary microscope. But despite its size, figuring out this hidden world has honestly been the ultimate scientific detective story. Over centuries, brilliant minds have slowly pieced together the clues to figure out exactly what makes up the matter all around us, from the air we breathe to the rocks on the ground, all the way to our very own bodies.
To kick off our investigation, I want you to try a little thought experiment with me. Imagine you have a single drop of water. Now you divide it in half. Then you divide that in half again. And you just keep dividing it into smaller and smaller parts. What do you eventually get? Like, is there a limit? Do you eventually hit a particle so incredibly tiny that it literally just cannot be broken down any further? Well, this exact philosophical question is what originally sparked the curiosity of our ancient ancestors, and it really kicked off this entire journey.
And man, what a journey it's been. As you can see on this timeline, for over 2,000 years, the idea of tiny, indivisible particles was just that, a philosophical musing. But look at what happens once we hit the 19th century. Once we actually gain the ability to run real experiments, the timeline just compresses into this rapid-fire series of scientific breakthroughs. In barely over a century, we went from thinking of atoms as these basic solid spheres to mapping out highly complex internal energy levels.
All right, let's dive into Section 1, Early Thoughts on Matter. Basically, the philosophical era.
So, picture this. More than 2,000 years ago, two totally distinct cultures were actually asking that exact same question about dividing matter. Over in India, the philosopher Acharya Kannada proposed that eventually you'd reach a stage where particles just couldn't be divided anymore. He called this absolute smallest particle Parmanu, and he noted that all matter is just combinations of these Parmanus. Around the exact same time, Greek philosophers Leucippus and Democritus proposed a virtually identical idea. They called their tiny particles atomos, which is Greek for indivisible. They even brilliantly deduced that different substances must contain different kinds of atoms. But of course, there was a catch. Both of these ideas were purely philosophical. Neither had any actual experimental proof to back them up.
So, we fast forward all the way to 1808, and we finally get some hard science. Enter John Dalton and his atomic theory. He laid out a really firm set of rules. First, he stated that all matter is made of tiny atoms, and, crucially, he agreed with the ancients on this one. Atoms are strictly indivisible. You cannot break them down into smaller parts. Period. He also figured out that atoms of the same element, say all hydrogen atoms, are perfectly identical to each other, but they're completely different from, say, oxygen atoms in their mass and properties. Finally, he noted that atoms combine in fixed ratios, so water, for example, always contains hydrogen and oxygen in one specific fixed ratio.
Now, Dalton's theory was a massive leap forward for science. Yes, it was brilliant, but it had a really critical limitation. Are atoms truly indivisible? Like, was Dalton right that absolutely nothing exists that's smaller than an atom? Well, his theory couldn't explain stuff like radioactivity, and it couldn't explain the internal structure of the atom. And that is because, spoiler alert, atoms actually aren't the smallest things in the universe.
Which brings us nicely to Section 2, discovering the first subatomic particle. In 1897, a scientist named J.J. Thomson ran this absolutely brilliant experiment using what's called a cathode ray tube. He took this glass tube filled with gas at a really low pressure, and he applied a super high voltage across two metal electrodes, a negative cathode and a positive anode. When he did this, he observed these rays traveling in straight lines from the negative side to the positive side. But here is where it gets super interesting. When he introduced charged metal plates near the tube, those rays deflected away from the negative plate and pulled toward the positive plate. Since we all know opposites attract, Thomson realized these rays weren't just light. They were actually a stream of tiny, negatively charged particles. He called them electrons.
And you guys, this was a massive turning point in our detective story. Atoms are not indivisible. J.J. Thomson literally proved they contain these tiny, negatively charged electrons inside them. And because they contain electrons, it means that atoms themselves can be divided. They actually have an internal structure. This was a monumental discovery that led Thomson to propose his famous plum pudding model, and it essentially marked the official birth of modern atomic theory.
But you know how science works. Solving one mystery just creates another one. We know atoms as a whole are neutral, right? So if they have these negative electrons swimming around inside them, where exactly is the positive charge to balance it all out? What does the rest of the atom actually look like?
Let's move on to Section 3, Rutherford's empty space atom.
Okay, so in 1911, Ernest Rutherford sets up what is now famously known as the gold foil experiment. He takes a narrow beam of positively charged alpha particles and shoots it directly at an incredibly thin sheet of gold foil. He put a fluorescent screen all around it just to track where the particles ended up. And what he observed totally changed the game. First, most of the particles passed straight through the foil like nothing was even there. This meant that the vast majority of an atom is actually just empty space. But some particles deflected at small angles. This told him the positive charge wasn't just spread out evenly, it was concentrated. And then, the absolute biggest shocker. An incredibly tiny fraction of those particles bounced straight back toward the source. From this, Rutherford deduced that the center of the atom must be unimaginably small, super dense, and positively charged. He had just discovered the nucleus.
Just to truly wrap your head around Rutherford's discovery, I want you to think about the number 100,000. Rutherford calculated that the dense nucleus sitting at the center of the atom is about 100,000 times smaller than the total width of the atom itself. That scale is just wild. To put it in perspective, if an atom was the size of a massive football stadium, the nucleus would literally be the size of a tiny marble sitting right on the 50-yard line. Everything else, just empty space.
So based on this mind-blowing data, Rutherford proposed his planetary model. He stated that you've got this tiny central nucleus holding all the positive charge and practically all of the mass of the atom. Surrounding that is just vast empty space, and out in that space, those tiny electrons are revolving around the nucleus in circular paths, honestly very much like planets orbiting around the sun.
Now, it's a beautifully simple model, for sure, yes, but it had a rather fatal flaw. You see, according to the laws of physics, if electrons are continuously moving around in circular paths, they should be constantly losing energy. And if they're losing energy, they should inevitably spiral inward and just crash straight into the nucleus. If that actually happened, all atoms would just collapse instantly. But since we're all sitting here, and matter is clearly stable, Rutherford's planetary model totally failed to explain why those electrons don't just fall into the nucleus.
Enter Niels Bohr. Section 4. Bohr's fixed energy levels.
So, in 1913, Niels Bohr steps up with a really elegant solution to this problem. He proposes a new atomic model stating that electrons revolve around the nucleus only in certain specific fixed circular paths. He called these paths orbits, or shells, and here's the absolute magic of it. Every single shell has a fixed, definite amount of energy. As long as an electron stays in its designated orbit, it simply does not lose energy while revolving, and that right there is why the atom is stable. He also added that electrons can actually jump from a lower energy shell to a higher one if they absorb energy, and they can drop back down by releasing energy, which we often see in the form of light.
But Bohr didn't just say, hey, shells exist. He actually mapped out the rules for them. Moving outward from the nucleus, he named these shells K, L, M, and N. Using a formula called the Bohr-Bury rule, you can figure out the maximum number of electrons allowed in any shell just by using the math, 2n squared, where n is the shell number. So shell number 1, the K shell, can only hold 2 electrons. The second one, L, holds 8. The third one, M, holds 18, and so on. It's like a highly organized apartment building with a strict occupancy limit for every floor. This mathematical architecture became the foundation for understanding how electrons are arranged across all the different elements.
Okay, let's transition from the history into the practical stuff. Section 5, Decoding the Atom's Anatomy.
To really understand how atoms behave out in the real world, we need to get down to super important terms. First up is the atomic number, which we represent with the letter Z. This is simply the number of protons sitting right there in the nucleus. Think of it as the atom's ultimate ID card. Literally, no two elements have the same atomic number. Oh, and by the way, in a neutral atom, the number of electrons perfectly matches this number of protons. The second term is the mass number, represented by A. This is the total head count of the heavy stuff inside the nucleus, so the protons plus the neutrons.
To see how this plays out, let's look at a few examples. Take carbon-12. It has an atomic number of 6, which means 6 protons. If its mass number is 12, well, it must have 6 neutrons to make up that difference. Simple math, right? Oxygen-16 has 8 protons and a mass of 16, so boom, 8 neutrons. Sodium-23 is kind of fun. It has an atomic number of 11, so 11 protons, but a mass of 23. If you just subtract the atomic number from the mass number, you easily calculate that sodium has 12 neutrons.
All right, so we know what's inside the atom, but how do they actually interact with each other? That all comes down to valency.
Valency is basically the combining capacity of an atom. You see, atoms just want to be stable, and they are at their most stable when their outermost shell is completely full. Usually they need 8 electrons to complete an octet. To reach this happy stable state, atoms will actively lose, gain, or share electrons. For example, argon's outer shell is already totally complete, so it doesn't need to do anything. Its valency is 0. Carbon has 4 electrons in its outer shell, so it's looking for 4 more to finish its set, giving it a valency of 4. Sodium, on the other hand, has one single pesky extra electron in its outer shell that it desperately wants to lose so it can drop down to a stable full shell, so it has a valency of 1.
Now we need to clear up 2 terms that people mix up literally all the time. First, we have isotopes. These are atoms of the exact same element, meaning they have the exact same number of protons and behave exactly the same chemically, but they have a totally different mass number because they have a different number of neutrons. And isotopes are incredibly useful. Uranium-235 is used as nuclear fuel. Cobalt-60 is used to treat cancer, iodine-131 treats thyroid disorders, and carbon-14 is how we date ancient fossils. On the flip side, we have isobars. These are completely different elements with completely different atomic numbers, but by pure mathematical coincidence, their total mass number happens to be exactly the same. Since they are different elements, they have completely different chemical properties.
Wow, okay. We've come incredibly far from those early days of philosophical guesses, haven't we? We've gone from Dalton's solid spheres to Thomson's little electrons, through Rutherford's empty space, and finally to Bohr's highly organized energy shells. But you know, our detective story doesn't actually end here. Bohr's model was great, but it had its own limitations. It worked perfectly for simple atoms like hydrogen, but it kind of fell apart when explaining the behavior of electrons in complex atoms. Plus, it couldn't really explain why electrons were restricted to those fixed orbits in the first place. Eventually, Bohr's model had to be replaced by the modern quantum mechanical model, because as it turns out, the closer we look, the more bizarre and complex our universe really becomes. So, the final question I want to leave you with today is this: what mind-bending mysteries are we going to find when we zoom even further into the quantum realm?